An early example of a steam engine, called a Hero's engine, consists of a spherical shell filled with steam as shown in the figure to the right. Two nozzles direct steam exhaust in opposite directions. Ooh, two nozzles, okay, that's important. Arg! Ah! Pump, pump, two. In opposite directions, causing the shell to rotate about an axis through its center. The spherical shell has a mass of 0.7 kilograms and a radius of 0.3 meters. Assuming for simplicity that the nozzles have negligible mass. Each nozzle generates a thrust force of 4.3 newtons. How long does it take for the engine to make one rotation when started from rest? Okay, heat source, reservoir / boiler / engine, and it shoots out steam. Yep. Okay, so your first thought here should be kinematic equations. So you're like, all right, if this was linear, then we'd do force equals mass times acceleration. And then we'd use A equals A, V equals AT plus V naught, and X equals 1/2 AT squared plus V naught T plus X naught. And so you're like, well, this is how I do it linearly. How would I do it using angular, rotational? And what you do is you basically just look at it as the analog. As an analog, the angular analog of linear. So torque equals moment of inertia times alpha, where moment of inertia stands in for mass, and alpha is the angular acceleration as opposed to linear acceleration. And we also know that is r cross f, so probably something like this. And we know that r and f are perpendicular to each other. So this cross product is just going to be a sine of 90 degrees, which is 1. And so we're going to be left with moment of inertia times angular acceleration will be radius, magnitude of the radius times the magnitude of the total force. I'm going to write total down here because we know that there are two nozzles here, each contributing 4.3, and we don't want to forget that there's two of them. Okay. We also know that x equals r theta, v equals r omega, and acceleration equals r angular acceleration. We start with this one because that's the easiest one to conceptually understand. You say, all right, I have a circle. There are 2 pi radians in the circle. Multiply that by r, and that's going to be the same as the circumference of the circle, which is also 2 pi r. So like, okay, that one sort of makes sense. And then you can take the derivative with respect to time of each of them, and you derive those the same. You just derive one after the other. So velocity is time derivative of x, and acceleration is the time derivative of v. And that's kind of the way these play out. Not saying you should derive them every time, but they should be conceptually comfortable for you. Okay, so now that we have that, we can plug these into this, and skipping to the end, you're going to get something along the lines of theta final equals 1/2 alpha t squared, t stays the same, plus omega naught t plus theta initial. So when you plug them in, you get a whole bunch of r's, all the r's cancel, and you're left with an equation that looks very similar to your linear kinematic equation. Like, okay, we're fine here. So now what we want to do is we want to find some of the values here. So we know we start from rest. Make sure real quick, starts from rest. Means that the initial angular speed is 0. We're going to assume that it's trying to make one rotation. So we're just going to say it arbitrarily starts at 0 because we're not really looking for theta. We're looking for delta theta. So calling it 0 is fine. Alpha, we have this idea over here of force equals ma, which we then kind of rewrote a few times to get moment of inertia times alpha equals radius times force total. So I'm going to rewrite that in terms of alpha equals r times force total. Yep, r times force total. Radius times force total over moment of inertia. So the moment of inertia for a hollow cylinder is 2/3 mr squared. You'll just probably be given this. I would be surprised if you're expected to memorize it. This will be, I'm just going to write this out. I know I could probably cancel the r's, but I'm just going to try and, to keep me from making mistakes, write everything out. So we have 0.13, which is the radius, times 2, because we have two sources of force, times 4.3 newtons, which is the force of each newton, times 2/3, times the mass, which is 0.7, times r squared, which is 0.13 squared. Okay? Okay. Keep going through this. Maybe do a little bit of canceling. So we'll do a 2 there. Move the 3 up here. Cancel one of the r's, and we're left with 3 times 4.3 all over 0.7 divided by 0.13. Okay? I could do that in my head. I'm not going to. On clear, 3 times 4.3 divided by 0.7, makes it a little bit bigger, divided by 0.13, which is the radius. We have 141.76. 141.76. This is going to be radians per second squared. That's the acceleration of this Hero sphere. Hero engine. Okay, so we have that. So now we're going to take our kinematic equation, which we've pared down significantly, and we're going to solve for t squared. So t squared equals 2 theta final all over alpha, which is going to be 2. And in the theta, it's going to be 1 revolution, and 1 revolution is 2 pi. And it's going to be over 141.7 something something something. And we get an answer like, so we do 2 times 3.1415, yes, divided by second answer. That's going to be our t squared, second square root, second answer, and as you get closer to 1, we get 0.2105. T equals 0.2105, and this will be measured in seconds. So, let's see if it's a possible answer. 0.2, no, did I mess this up? Maybe. Let me check this over again real quick. 2 times 2 pi, I messed up there. Okay, so up here, 2 times 2 pi, I forgot a 2, 3.1415, divided by 141.758. Okay, see, and then second square root, second answer, 0.2977. Okay, 2977. There we go. Whoop, whoop, look over here. And D, right here. Possible answer, D equals 2.98. Okay, so to backtrack, kind of see what we did here. We had, yep. We were given a rotating object. We're asked how long does it take to move one rotation? And we're given a force. So when you hear force, you should think, okay, acceleration. And when you hear time, how long does it take to go this distance? You should immediately think your kinematic equations. So what I would do is I would write up force equals ma, then I'd write up my kinematic equation. I'd then write the analog equivalence, or the angular equivalence of these. So you have torque equals moment of inertia times alpha, which I is sort of like mass, angular acceleration is kind of like linear acceleration, and that also equals r cross f. One key thing to make sure here is your force is going to be 2 times the force I gave you because there are 2 nozzles. You then rewrite your kinematic equation for distance in terms of angular. Cancel out the zeros. You then rearrange to find the acceleration. Use the angular moment of inertia. And do your algebra. Don't forget numbers like I did. Always happens. And eventually you get an answer. So not too complicated, but considering you only have a couple minutes to do it, that's a lot of things to jump through. And it's important to have the idea, the cues in your head of where to go. Force implies acceleration. Distance travel or time to travel a distance implies kinematic equations. And you just kind of skip one stone across the other and eventually get to an answer. Okay, now number 15. Now suppose the nozzles have masses and are no longer negligible. How would the time above change? Okay, so what this would do is this would change your moment of inertia right here. The moment of inertia would go up, which means your acceleration would go down. And if you have lower acceleration, it's going to take you longer to get a specific distance. And so longer to get a specific distance would imply that the time required would increase. So that's how I would approach this problem. I hope that helped, and I will see you next time.